Morning, everyone. So we've reached the end of our electrochemistry chapter. I was hoping just to summarize over some of the main concepts for you here. For electrochemistry, we've been looking at the interplay between sort of electricity and chemistry. At first, we started running spontaneous chemical reactions, and we used that to actually generate a positive voltage. Those were called Voltaic cells or electrochemical cells. Towards the end of the chapter, we actually use electricity to actually cause a non-spontaneous reaction to occur, but it is just sort of this changing of chemical energy to electrical and vice versa. The main type of reaction that we're interested in is referred to as a redox reaction. A redox reaction essentially is a reaction that ends up transferring electrons. So, transferring electrons between the species, the chemical that is oxidized. So that is one part of the equation. So that's this ox part. Remember, we had the little memory aid here. Leo the lion says grrr. So the species that was oxidized is the thing that has actually lost electrons. And for that one, electrons on the product side. Right. So having lost electrons, I would release these electrons. Electrons are charged. In general, I don't want to have any free charges in nature. What's going to end up happening is we actually want to transfer those electrons to someone else that's willing to pick it up. That's where we actually have this gain of electrons to another species who's reduced. And the reduced species, normally when things gain, we expect them to go up. It just turns out the things that we're gaining actually happen to have a negative charge. The thing that's actually going down is actually the total charge. So gain electrons, we're going to have electrons on the reactant side. For the half equations, you can still have free electrons, it's fine. But overall, we had worked out lowest common multiple so that all the electrons were passed from the species oxidized to the species that was reduced. So, case in point here, let's take a look at an example. We're going to take lead ions, and we're going to react them with iodide ions and end up forming PbI2. First style of question can be, is this a redox reaction or not? Okay. The best way to tell whether this is a redox reaction or not is to check something called oxidation number. Oxidation number pretends things are ionic. If we find that the oxidation number goes up, oxidation. If it goes down, it's going to be a reduction. So we found that there was a whole list of rules here. If we had an elemental state, we had just called it 0. Well, nothing's elemental here. If it was a simple ion, we just gave it its charge. So I have two simple ions here. Pb is +2. If I pretend it's ionic, well, that's basically +2. Iodide is -1. Well, that's basically -1. How about in compound here? Well, the lead is still +2, and the iodide is still -1. Oxidation number here, it does have to be the sign first, then the digit after, the number after. They're actually going to mark you wrong if you put 1 minus or 2 plus like that. So I generally tell people just always put the sign first. In many cases, it actually doesn't matter, but in the times that it matters, like oxidation state, you have it right. We saw a rule that the overall charge, in this case here, is 0. Well, +2 times 2 times -1 gives you 0. That's perfect. So we cancel out the charges. In this case here, the lead is still saying 2 and 2. The iodide is 1 and 1. Because there is no change in oxidation number or oxidation state, this is not a redox reaction. And we've actually learned quite a lot of reactions that aren't redox. We've learned synthesis reactions, decomposition reactions. We've learned acid-base neutralization. Those are other reactions that do not involve electron transfer. When would an electron be transferred? Since an elemental state here would be 0, what if I swap this out here? And what if I put, let's say, lead solid and I react it with iodine? This time, if you follow your rules, well, because they're elemental, lead is a 0 state. Iodine here, although it's diatomic, each iodine, oxidation state is defined per atom. Each iodine here is actually a 0 state. So going from the elemental state to its being charged state, Pb is +2 and I is sort of like a -1, then I can actually track the change. If lead goes from 0 to +1, anytime your oxidation number goes up, we know it's oxidation. Leo the lion says grr. That means we have lost electrons. I had to throw away negative things for my charge to go up. I would expect the other guy to actually having gained electrons, going from like a 0 to a -1. Whenever your oxidation number goes down, we know it's reduction. We've actually gained electrons. So how has the electrons been transferred? Well, we have transferred from the person that lost it. Lead has passed some of its electrons over to the iodine, and therefore letting the iodine reduce. Okay. Now this equation here is already balanced. In terms of balancing, we always want to balance for number of atoms, just like we usually do. Make sure all the atoms are accounted for. And in this case here, because we're dealing with charges that are passing around, we also want to balance for number of charges as well. And we learned sort of two systematic ways. One was half reaction method, the other was oxidation number method. I'm going to walk you through those again. Just before we do that, there is one other terminology here. They might ask you here, define an oxidizing agent. Okay. Remember, as an agent, this is a chemical that allows something else to oxidize. So a species that helps another oxidize. That's its job. It helps someone else lose electrons. But strangely enough, in the process, itself gets reduced. If I'm asking you to define oxidizing agent, don't just tell me, oh, it's the thing that gets reduced, right? Even though usually that is a hint and it helps point you which one's the oxidizing agent. Think about in this situation, these things here are always referring to reactants. Well, in our problem, lead got oxidized. Who is present to actually allow the lead to oxidize? If lead wants to lose electrons, who is willing to pick up the electrons? Well, it was iodine. Iodine here not only is the chemical that was reduced, iodine here is actually the oxidizing agent. In a similar fashion here, a reducing agent, if you're going to define it, it's a chemical that helps something else reduce. In this case, I2 gets reduced. Were it not for the lead that was willing to pass its electrons, I2 would sit around forever and it wouldn't actually pick up electrons unless the lead was there. So the reducing agent in this case here is going to be the Pb. The Pb, which ends up getting oxidized, is also equally the reducing agent. Notice when you're just sort of identifying those ones there, we are only looking at reactants. I could care less what the products are. After the electrons get transferred, we happen to produce Pb2. Who cares? But on the left-hand side here, I want to know who had gained electrons and who had lost electrons. Right? So I'm just going to pull out an equation here. I'm going to demonstrate for you both methods of balancing. So let's say the question is just worded here. I want you to balance Cl2 and SO2 becoming Cl minus and SO4 minus 2. We had two strategies of doing this. One strategy here was half reaction method. They're not going to force you one way or the other. The other one, as I alluded to here, is oxidation number method. If the question is just asking who got oxidized, who got reduced, I would prefer oxidation number method because, as you find, half reaction method here is very tedious and it takes up a lot of room. But let's just go through here. In both cases, you have to balance the major atoms first. Major atoms are everything that's not O or H. In this case, I have Cl2. I only have one chlorine there. Right away, I need to put a 2. Sulfur is a major atom, so it's one sulfur, one sulfur. Sulfurs are good. Then for the rest of half reaction method, because we are talking about half reactions, we're breaking up the two half equations. Chlorine probably becomes the other chlorine-looking compound. The sulfur compound, SO2, probably becomes the other sulfur-looking compound. The goal here was to balance off the half reaction, make both half reactions match up, and then put it back together with lowest common multiple. We had done sort of major hydroxide. I already balanced my major atoms. I'm going to balance off my oxygens by adding water. Right. Most of these reactions take place in aqueous solution. I balance the hydrogens by adding H+, and I balance the charges by adding electrons in that order. So I already balanced my major atoms. I have no O's, H's, so that's already balanced. I need balance for charge. The total charge on the left is 0. The total charge on the right, every chloride has a negative, but there's 2 of them, so that's going to give you 2 minus. I want to add 2 electrons to the left-hand side. How about the other equation here? The sulfurs are balanced, the majors are balanced. I have 2 O's, I have 4 O's. Don't care about the charge right now. I need to add 2 waters to the left-hand side. That will at least give me 2 O's, 2 O's, so 4 O's and 4 O's. That matches up. 2 times 2 ends up giving you 4 H's. I have no H's yet, plus 4H+. A lot of these solutions take place in acidic. If they don't specify, assume it's acidic. I'll show you the basic step later on. And then I want to balance for total charge. The total charge on the left here, both of these are neutral, 0. The total charge here, I have a negative 2. Every H is a positive, but I have 4 of them. Total charge here is actually a positive 2. I'm going to want to add 2 electrons so that 0 matches up with 0. They don't actually have to cancel out, but they have to be the same on both sides. we would normally need to do a lowest common multiple between them, make sure there's no free electrons in nature. This time 2 and 2 just come together here, so there's no scaling of the equation at all, and then all we have to do is we need to put everything on the left side, Cl2 and SO2, order doesn't matter, plus 2 waters, and it ends up giving you here 2 Cl minus, a sulfate, and a 4H plus. That's equation now should be balanced in terms of number. I usually run out of time here, so I usually just check the charges. I have 2 minus from there, minus another 2 is -4, plus those 4 is 0 and 0. We're probably balanced. Oxidation number method here, first step, we're actually not going to break up the overall equation. We're just going to identify the oxidation numbers of everything present. Well, this chloride here is a 0 oxidation state. This chloride is a -1. I don't worry about that 2 there. When I go from 0 to -1, I've dropped by 1. But because oxidation number here is per atom, you'll notice having 2 chlorine atoms, both of which end up going to Cl minus, I actually drop by 1 for this chlorine, and I also drop by 1 by this chlorine. So in total, this has already become a drop by 2. Even before worrying about lowest common multiple or anything like that, every time one of these Cl2s become 2 chloride, I have already equivalent of losing 2 electrons. Because my oxidation number has dropped, I know my chloride, the reactant involved, has been reduced. That must mean the SO2 is oxidized. I would expect the oxidation number to go up. Let's check it here. So oxygen here is -2 times 2, -4. Sulfur is like in the +4 state. Later on, oxygen -2 times 4 is -8. Sulfur is in the +6 state. Lo and behold, going from 4 to 6, it actually is a gain of 2. That actually refers to an oxidation. Normally, we would do a lowest common multiple between this 2 and 2. Well, this one here already matches out, so I don't need to balance anything else. The advantage here is I didn't break up half equations. So all I'm going to do is I'm going to still add in the waters to balance the O's, add in the H pluses to balance the H's, but I'm doing that to the whole equation so that I don't end up with waters on both sides and canceling out and H plus on both sides. Let's just match it up here. I have 2 O's on the left, I have 4 O's on the right. Let's just go ahead and add 2 waters on the left-hand side. Now I've made 4 H's, I have no H's on this side. By the time you add 4 H pluses, you notice that this one here is already balanced. And you see that sort of in comparison, it's actually a little bit quicker. Okay. So in terms of our major hydroxide mnemonic, we had balanced the major atoms first. That's always the first step. By figuring out these oxidation number changes, by matching up oxidation numbers, we've actually somehow balanced the charges first, and then you add the oxygens, add the waters to balance the oxygens, add the H pluses to balance the hydrogens. Okay. Again, you can assume that these are acidic solution. What if I said basic? You do everything like we just did. This is so far for acidic. To convert an acidic equation to a basic equation, you have one of 2 ways of doing it. If I want basic, the way I do it here is I pretend, well, basic means I don't have an excess of H plus. Imagine adding 4 OH minus. What you do to one side, you have to do to the other side. Yes, the H plus cancels out the OH minus, but it doesn't disappear. That ends up forming 4 waters. If I can cancel out some of those waters here, I have 2 waters and I have 4 there. Let's just make that a 2. Now I have the equation as written in basic, and therefore this one here should also be balanced. That's one way of doing it here. So if they add that basic parentheses here, you do need to do this one extra step. The other way you can do it is you can add the self-ionization of water. Well, I have 4H plus here. What if I added 4H plus and 4H minus? That neutralizes to give 4 waters. That way, right side cancels left side. The H pluses are gone. That's also going to give me the 4 hydroxide on the right, on the left hand side. On the right hand side, I have 4 waters. That cancels these 2 waters here. I have 2. I'm going to end up with exactly the same expression there. Okay. So whichever one you're more comfortable with here, that's the way you balance. Okay. Then what we did is we started looking at the redox table. Okay. The redox table here is very similar to the acid-base table. We write everything. The title here is actually a standard reduction potential. This standard is usually symbolized by a naught symbol. So when I have that standard potential, this is E naught. Standard actually implies solutions are 1 molar, the temperature we're at is 25 degrees, the pressure we're at is 1 bar. That way I can make a fair comparison between all these chemicals, right? They're written as reductions. So I have the chemical. As a reduction, electrons are going to be on the left side. All of these are written as equilibrium arrow. We had actually ordered them, just like our acid-base table, these are going to be the oxidizing agents. Remember, the oxidizing agents are the chemicals that actually reduce. And we had the strongest oxidizing agents, the best at reducing, are the ones that are highest on this table. So as a general rule, whether we were talking about a voltaic cell or electrolytic cell here, we always start from the top left, and you want to find your first match. Once you find your match, this is the guy that's going to do the reduction. I don't care how many other guys you have in the mix. Those ones that are just going to be spectators. That's only half the equation, though. The potential here, which is listed for you as an E0, is the potential for you going left to right. Let me just write out an equation for you here. On the table, we might find sort of partway down the table, let's do Fe plus 3 gains an electron, one-way arrow ends up becoming Fe plus 2. That voltage here is a positive 0.77. Right? Technically, if it's just a half cell, I shouldn't be able to do a voltage. I can't just have something sitting around waiting to get an electron if nobody's willing to actually give it its electron. So what this 0.77 actually refers to is actually our standard hydrogen electrode. In the middle of the table, we have 2H plus and 2 electrons in equilibrium giving you H2. That actually is 0 volts. So what we do is we actually set this as our reference. This reference here is a standard hydrogen electrode. We call it the SHE, the standard hydrogen electrode. Sometimes they do ask you to draw this out, so you want to be comfortable with this one here. This one here is a half cell. On the one side, we have hydrogen as a gas, so I need a contraption here to actually bubble in gas. Whether I'm going to bubble in H2 or H2 is going to be bubbled off. We're going to typically use an inert catalyst, an inert electrode. Inert electrodes, as we've seen, they basically are so bad at oxidizing and reducing, they just sit around. The two that we had were either platinum or carbon. So this is just a temporary holding place for electrons. Let's say I bubble in hydrogen. Hydrogen, upon touching this platinum, it drops off its electrons and actually releases H plus in solution. So H plus, it's going to be 1 molar, so that we're at standard state. This is the standard hydrogen half cell. When I hook up my iron cell, relative to the hydrogen cell, the iron cell is positive 0.77, better at reducing than H plus. Notice I'm looking at the left-hand side here. Okay. As I start going lower than it, let's just pick another reaction here. Let's say chromium, upon gaining an electron, that's in equilibrium with Cr. This one here is a voltage of negative 0.41. Well, what good is a battery if it's giving you negative voltage? That negative here just means, it's still a positive voltage, but that negative just means it's 0.41 volts worse than the SHE. Okay? So we just arbitrarily set one to be our reference. Some of them are better at reducing. It forces the hydrogen to actually oxidize. Some are actually worse at reducing, so the H plus gets to reduce, the other has to oxidize. Okay. Couple rules for this potential. Again, that word potential here is the word for voltage. Right now, these are all written for reduction potential. So all these numbers are written for left to right. Anytime you want to go right to left, so if I want to go oxidation, oxidation is on the table right to left. I want you to flip the sign. So if we were positive 0.77 going from iron 3 to iron 2, if I go backwards, Fe plus 2 to Fe plus 3, that's going to be a negative 0.77. So you flip the sign. If you scale the equation, this E0 is unchanged. So E0 is unchanged when scaled. And what I mean by that here is when we were doing balancing here, sometimes for lowest common multiple, we had to go like, oh, the whole equation times 3 or the whole equation times 2 or whatnot. In some sense, when you run the reaction 3 times, you are getting 3 times the energy. It just turns out when you do this voltage is actually energy per charge carrier. You may have tripled it and you may have gotten 3 times the energy, but also tripled the number of charge carriers. That ratio there ends up the same. So long story short, this voltage here doesn't change. Okay. Just to get rid of that 3 just so that we don't get confused. So that one there is unchanged. The overall E cell from the battery is actually both sides. So we're going to have E cell, the total voltage, is actually going to be, if it's positive, it's a spontaneous reaction. This one is a working battery. If it's negative, it's like those electrolytic systems as a non-spontaneous. So let me just sort of recap with you in terms of the spontaneity bit here. We started looking at electrochemical cells. Nowadays, they use this term here, electrochemical cell here, as the umbrella term. I want to just summarize for you first types of cells here, we called that were voltaic cells, also called galvanic cells or Daniell cells. These ones here, a voltaic cell, we're going to run a spontaneous chemical reaction to produce electricity in the terms of voltage. Because the reaction was spontaneous, I want to be able to taper off this energy. I had to run it in 2 beakers. So that's a nice hint here for it being a voltaic cell or electrochemical cell. We have one metal plate here that's going to be called the anode. The anode, by definition, again, we have our mnemonic here, anox cared. Okay. Anode is always the site of oxidation. This is where things lose electrons. The anode, for all I care, could be an inert plate. It could be platinum, could be carbon. It's just a temporary holding place for those electrons. Maybe I have other chemicals here. They swim up close to this plate here. They drop off its electrons here, and then they end up leaving solution. That's fine. As long as the platinum can temporarily hold the electron, it's still the location for oxidation, so it's still called the anode. The cathode is the opposite then. The cathode is going to be the location, the site of reduction. It's the location where I actually pick up electrons. Because I set these up in 2 half cells, I force the electrons. Electrons always flow. This is true for both types of cells. Electrons flow from anode to cathode. But here's the emphasis here, through the wire. Electrons never enter solution. They get dropped off on one side through an external wire that hooks up from one side to the other. Electrons only jump through the wire. They always try to trick you every now and then. They say, oh, do electrons enter solution? No, they don't. Okay. Because I have electrons flowing, I have a direct current. I would stick my light bulb or buzzer or whatnot, my electrical device, in between and actually taper that electrical energy. It's spontaneous, but I force the electrons to have to go through the wire. We saw a problem for these voltaic cells here. If you just did this in the lab here, one side would typically be losing the positives, one side would be losing the negatives. Both sides are sort of at risk of becoming overly charged. What we needed for this one here was actually adding in a salt bridge. A salt bridge can be as simple as maybe a U-shaped tube here. You fill it up with a little bit of salt. We're going to still have 1 molar solution. Very often we use KNO3. If you find that on the table, you're going to find that it's so far down on the left, it's so far up on the right that this actually doesn't interfere. And all it's going to do is it's going to help maintain charge balance here. Let's say K+. K+ is a cation. Cations are generally going to go towards the cathode side. So on this side here, let's say my reaction was copper ions are swimming up close, they're picking up electrons, they actually solidify to become copper solid. The mass of this cathode actually increases. That's almost like an electroplating process here. I'm at risk of losing over too many positives. Well, what if the K+ also jumped into solution? There's a tendency to actually head that way. Cations go towards cathode. Whereas if it was an anion, anions tend to want to go towards the anode. So if I have an anion like NO3-, the other side here, it's losing its electrons. The electrons are actually leaving. These NO3- end up going to the left-hand side. So it's going to, anions go towards the anode. There is argument for if I have a sort of like a cotton plug to make sure the solution can actually stay in there. If the ion is too big, it can't actually travel through the salt bridge, but there is this tendency. Cations towards cathode, anions towards anode. Okay. The overall voltage is going to end up positive, spontaneous. I was able to taper the electrical energy. This is actually what's happening inside a battery. Right. Now, as all batteries here, as you run it for long periods of time, the chemicals end up depleting, and as the chemicals deplete, the overall voltage drops down to 0. When I have a dead battery, we're at equilibrium. We actually don't have a situation for it to actually react anymore. On the other type of electrochemical cell here, we have actually what's referred to as electrolytic cell. We had categorized this in terms of type 1, type 2, type 3. I just want to emphasize here for a type 1 cell. Type 1 cell, we use the word here molten. The emphasis there is that there's no water. Water is really annoying in this section because water actually appears, it can actually reduce, it can actually oxidize. If I really want some of these really bad at reducing, really bad at oxidizing species to actually react, I want to make sure I've melted it. It's like having a lava or a liquid. There's no water present, so the ions themselves can actually react. And as you did here, as you went to type 2, type 2 essentially started adding in some aqueous salts. So now that we have water, water usually interferes, and type 3, we're going to have reacting electrodes. But in general, for electrolytic cell, we have to, well, it's a non-spontaneous reaction. We're going to actually use electrical energy, using electricity, using some external power supply to run a non-spontaneous reaction. So it's non-spontaneous, totally okay for you to just stay in one beaker, right? The chemicals don't naturally react. A battery doesn't simply recharge itself. But what I'm doing here is I'm going to put on an external power supply, any number of long lines and short lines. The long line is the positive side, the short line is negative. This is my power supply, external power supply. This is how I'm actually providing the voltage to actually cause the reaction to occur. The positive side is the anode side, still the site of oxidation. Electrons still flow anode to cathode. And basically, by the time we look on our table, we still do the same process. Start from the top left and go down, find your first match. It's just going to be really far down the table before I find my matches. If I find many things that can reduce, the strongest thing that can reduce is the one that's highest up on the table. Start from the bottom right and go upwards. Find an exact match here, right? By the time you find it, you're going to find water a couple times. So we have a water equation, we have another water, bunch of equations like that. By the time you actually find your matches, the oxidation reaction actually occurs above the reduction reaction. So when you actually calculate the overall E cell of this one here, you're going to end up getting a negative voltage, and that actually implies that it is non-spontaneous. Okay. One last note I want to imply to you here is, especially for the water equation, it has this funny bracket called an overpotential effect. And really, I've only seen them ask you questions. What if I had chloride and what if I had bromide here? If you were following this to the letter, the strongest guy oxidizing are the ones lowest down. I do run into water first. Experimentally, though, we end up finding chloride or bromide or anything else in the bracket technically should be worse off at oxidizing, but experimentally they actually oxidize before water does. So let me just make a note here. The species that are covered in the bracket, these species here experimentally, due to this overpotential, species experimentally oxidize before water. Right? And typically it's because we have a high concentration of chloride and a high concentration of bromide. Okay. We did do one application here with a redox titration. If you think about what is the redox titration trying to do, titration, again, is trying to find some unknown concentration. Right? Turns out the reaction that we're looking at here are these electron transfer reactions. One thing oxidize, one thing reduce. You can look up in our notes here. We typically use MnO4- because MnO4- is a really strong oxidizing agent. This thing here is actually going to reduce, and this thing here is actually helping me. It's going to oxidize something else, and it itself ends up getting reduced. We saw a similar reaction. Let's take this permanganate here. Let's do it. It's very often used for an iron titration, so let's just write out this equation. This equation will probably be balanced for you because they're testing you whether you know the redox titration part. If they wanted to ask you balancing, they'll ask that as a separate question. Right? So if you want to picture what's happening here, we're starting off in our burette. Our burette has a really deep purple permanganate solution. Right? I'm using that to actually count how much iron is in solution. So I have a bunch of these Fe+2s in solution. As long as I still have Fe+2, my purple droplet of permanganate will kill off the Fe+2, the overall solution stays colorless. As I hit the equivalence point, as I kill off all the iron +2, I'm going to drop in that one last drop of MnO4-. Now the MnO4- can't find any iron to react with, then the purple stays. This is sort of self-indicating. When the purple stays, it means I have leftover permanganate. That's when I stop. Okay. So it goes from deep purple. Fortunately, this Mn2+ form here is actually colorless, so I don't need any other external indicator. The other equation here was a little bit harder. The other indicator, or the other way we can set this up here, is using I- as a reducing agent. The reason why this one here was a little bit harder was because it actually takes place in two different steps. Okay, so let me just hint at how these steps go again. Step 1. what ends up happening here is we have something, let's say bleach, right? HOCl is going to react with 2I minus in becoming Cl minus, H2O, and I2, right? Step 1 actually converts all the I minus into the I2 form. In fact, I may not know the concentration of this HOCl here, so what we're going to toss in is an excess I minus. Usually this will actually require acidic conditions as well. Step 2, it seems counterproductive. We're going to then take step 2. I'm going to react all this I2 away, and I'm going to use sodium thiosulfate, 2S2O3. I'm going to be really careful with the titration on the this bottom equation here. So let's see what this looks like here. I'm going to have a solution here. This is my thiosulfate solution, S2O3. The only thing S2O3 minus will react with is actually iodine. The I2 have been created from the first step. So as long as S2O3 finds I2, the titration is not done yet. Usually what we use is a starch indicator. Starch and I2 complex ends up as a deep blue color. So you add starch, right? It already looks blue because I have a bunch of I2. You steadily drop in this thiosulfate, you steadily kill off the I2. Once all the I2 is gone, the starch can't complex with I2 anymore. It's not actually going to be a deep blue solution anymore. And in that situation, we're going to stop at that point there. I'm going to use probably my volume and my concentration. All titrations end up the same. We're going to then do a mole ratio. This is a mole ratio, moles to moles. That tells you how much I2 there was. But I2 was actually in a 1 to 2 ratio with your bleach. And that'll actually help you calculate back towards HOCl as well. Okay? So have another look at that there. This one, we definitely want it to be a spontaneous reaction, because I want it to be that when I drop it in, I want the chemicals to actually react. If the chemicals are actually non-spontaneous, if you could put these chemicals and they don't really care that each other are present, that wouldn't do any good. Okay? So have a look over some of these problems and just let me know if you have any questions. Thanks, guys.